Welcome to my math video for section 2.1, quadratic functions and models. And I figure I'd start this video showing an overview of all of chapter 2. Again, we're going to start 2.1 here. We'll spend a couple days on. And then we'll go on to 2.2, polynomial functions of higher degree. 2.3, polynomial division and synthetic division. 2.4, I believe in this we skip complex numbers. 2.5, the zeros of polynomial functions. I think that's more than 2 days. And then we'll do 2.6, rational functions, and 2.7, nonlinear inequalities. So let's dive right in. 2.1. In this section, we'll figure out how to analyze the graphs of quadratic functions, write quadratic functions in standard form, and use those results to sketch the graphs. And we can find minimum and maximum values of quadratic functions in real-life applications. And this is pretty straightforward. Remember, any quadratic, that's going to have a leading term of x squared. The graph is going to be shaped like a parabola opening up if it's a positive x squared. And it'll be opening down if it is a negative x squared. And when they talk about these minimum values, those only occur at the bottom of a valley. So an upward opening parabola will have a minimum value. And then they also talk about these maximum values, and maximums occur at tops of hills, and that would be on this peak of a parabola opening down. Okay. So here the book says, in this and the next section, we're going to study graphs of polynomial functions. Section 1.6, introduce basic functions such as linear, constant, and the squaring functions. Linear function right here, some number a times x to the first, and there might be a constant, could be a plus or minus. The constant function, notice here there's no variable, there's no x at all. This would just be a horizontal line. And then we have a squaring function, f of x is x squared. And then here in class, I always show you the strict mathematical book definitions, but then we always try to make it sound a little more simple. So here's how the book introduces this. It says a polynomial function. It says let n be a non-negative integer, so it's a whole number and it's positive. And then we have these a subscripts, a sub n minus 1, and that would keep going all the way over to a sub 2, a sub 1, a sub 0. Those are just real numbers. Our first one is not equal to 0, so that way it'll be well, here we got our function, and if I underline this as we go, I'll use red ink first. F of x is a sub n. That's just a constant in front of a variable x. And then here's another constant. The next one will have an a sub n minus 1, and then they'd go on n minus 2, and so on and so forth, till we get down to a sub 2, a sub 1, and a sub 0. And then as we go through the polynomial, let me switch to blue, and then we're going to have our exponents. Here's our base x to some power n, and that n will be the highest one. We always put the biggest exponent first, and then if there is one to one power lower, that'll be the next one. Here's n minus 1. And then we've got x to the n minus 2 power to the n minus 3, all the way down until we get down to x to the second, x to the first, and then here we have no x, or technically there's an x to the 0 on there, but remember, anything to the 0 power is equal to 1. So this last term at the very end is just a constant. And then that is the definition of a polynomial function of x of degree n. Or just a simpler way to think about it, a polynomial is going to be some constant, and then you're going to have x to an exponent, plus or minus some other constant with x maybe to 1 power lower, plus or minus another constant x to 1 power even lower than that, n minus 2. And there could be a whole bunch in there. I'll do dot, dot, dot. Maybe we start off at the 100th power, and we're going to go all the way down. And then eventually we'll get down to dot, 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 some constant x squared, plus or minus some constant x to the first, plus or minus maybe a constant at the end. And that's a polynomial in degree, or of a function in x of degree to the nth power. It's the highest degree is the degree of the polynomial. Polynomial functions are classified by degree. For example, a constant function, f of x is equal to c, and c is not, it's a number that's non-zero. It has degree 0, because I did mention earlier there could be an x to the 0 power in there, because that would just be equal to 1, and it wouldn't change the function at all. Our linear function, f of x, is ax plus b. That x has an exponent of the first power, and as long as our constant is not 0, that is first degree. In this section, we're going to study quadratics, which are second degree polynomials. For example, each function below is a quadratic. The first one really sticks out. You know, our first term is x squared. So we can really see it. Here, it's a little more hidden, but we have this x plus 1 quantity squared. If we did FOIL that out, we would have a leading term of x squared, and then it would get multiplied by this 2. So we would have some number, x squared, so that's a quadratic also. Now usually the exponent of the highest power goes first. Here they're trying to trick us. They got the constant first plus 1/4 x squared. Our highest power is x squared, so that's also a quadratic function. Here, the last one, k of x, you know, it's in two terms. If we did start to FOIL that out, let's FOIL it all the way out. I'm just having too much fun. If we do first times first, that will be x squared. Our outers will be a plus 1x. Our inners a minus 2x, so that's minus 1x. And then our last times last will be a minus 2. So now that we've FOILed it out, it looks a lot like the first one we saw. And our leading term is some number x squared, so that's also a quadratic. So now the definition on the other slide there, that was of any polynomial. Here's just a more stricter definition of just a quadratic function. And this one, it's a little easier to see what's going on. It just says a, b, and c are real numbers, and a is not equal to 0. If a is equal to 0, we would have 0x squared, so it would no longer be a quadratic, because a quadratic has to have a second power. So a quadratic here is some number a times x to the second, plus or minus some number b times x to the first. Now this b value could be 0, that's fine. And then plus or minus the constant c at the end, and that constant could also be 0. You know, a quadratic could just be x squared. F of x equals x squared, that's a quadratic. As long as we have something x to the second, it'll be classified as a quadratic. Often quadratic functions can model real-life data. For example, the table here below shows the height in feet of some projectile fired from an initial height of 6 feet with an initial velocity. Like let's say you're tall enough that your arm is about 6 feet off the ground, and you're going to throw a ball, and you throw that ball at 256 feet per second. The value stated in time t in seconds below, we have this quadratic function that models the data. And it starts out with negative 16t squared plus 256t. That 256 is the same from the initial velocity. And then we have a plus 6 constant, and that 6 is our initial height, where we were standing when we threw the ball. And it says this model works for all t values between 0 and 16. And what it says here, at time 0, if we draw a little graph here, at time 0, we're 6 feet off the ground. At time 4, you know, if we go out 4 seconds, and this will not be to scale, we're up at 774 feet. And then at 8 seconds, we're way up at 1,030 feet. 1,030, and we're way up here. Now notice when we come here at 12 seconds, so we go 4 more seconds in, and we're back down to the same height at 774. So our dot here will be at the same height as that one. And then we started at 6 feet off the ground, and here at 16, we're back to 6 feet off the ground. So at time 0, we were 6 feet. At time, this would be 16 seconds, we're back. If we start to connect the dots, now we're not sure that this point up here is the vertex. We don't have enough points, but we can just assume and say, okay, that's a quadratic. It has that parabola shape. You know, if we had more dots, we could be more sure. You know, maybe this went up a little bit higher, and then it had its peak there. You know, those 4-second jumps, we might have missed that peak, but I'll spill the beans in this case, we didn't. So these quadratics, they can model real life data. If you take calculus next year, we'll do a section where we do all kinds of real life applied problems, and you'll see that negative 16t squared a whole bunch of times. The graph of a quadratic function is a U-shaped curve called a parabola. Parabolas occur in many real-life applications, including those that involve reflective properties of satellite dishes and flashlight reflectors. You can study these properties in section 10.2. I don't think we get to that in this class. All parabolas are symmetric with respect to a line called the axis of symmetry, or simply the axis of the parabola. The point where the axis intersects the parabola is the vertex of that parabola. When that leading coefficient is positive of our quadratic here, that parabola opens up. When the leading coefficient is negative, the graph of the parabola opens down. The next two figures show the axes and the vertices for parabolas with our leading term positive and our leading term negative. So here on the left, it says opening upward, and we have our vertex. It is the lowest point. Our function here is a positive ax squared. And think about this, if we were to graph this point right here, let me use red ink. If we were going to graph this point, it would be, because we're left of the origin, the x value would be negative. That would be negative x, comma y. And here they have in this red dotted line, that is the axis of the parabola, or the axis of symmetry. And that's just going to be a line, x equals whatever this number is. In that ordered pair, that x value is going to be our axis of symmetry, because that's the vertical line splitting the parabola. To compare that, here when our a value is negative, this would be a negative ax squared, and our parabola opens downward. And for this one, if I highlight this dot in blue, if we were to graph that, it would be a negative x value and a positive y value, so something negative x comma y. And if they asked you a question, what is the axis of symmetry for this one? You could just write x equals whatever that negative number is. If this was a negative 2, you just say the axis of symmetry is x equals negative 2. The simplest type of quadratic function is the one where b and c are both equal to 0. In this case, the function is just ax squared. Its graph is the parabola. The vertex will be at the origin, 0, 0. Because b and c are equal to 0, these parabolas always go through the origin. When a is positive, the vertex point is the minimum y value of the graph. When the a value is negative, that means the parabola opens down, and we'll have a maximum value at the top of that hill. And we can see that here in the figures below. So here, if b and c are equal to 0, our parabola opens up. It will go through the origin, and this value is a minimum value. If our leading term is negative, our parabola opens downward over here in blue, and the dot right there at the origin will be the maximum. And then the book says below the graphs, when sketching the graph of ax squared, it's helpful to use the graph of y equals x squared, or 1x squared, as a reference, as suggested in section 1.7. There you learned that when the a value is greater than 1, the graph of this will be a vertical stretch, and when the a value is a fraction between 0 and 1, it will be a vertical shrink. And we'll see that here in example 1. Here, example 1, sketching graphs of quadratics. Part A, sketch the graph of the quadratic function. Compare it with y equals x squared. So if I do real quick here, x squared, oops, and I should have put this down here because this is definitely going to open up. Now the graph is going to be pretty crude, but we are going to go through the origin, and we're going to go through 1, 1, and negative 1, 1. And if we go out to 2, we'll have to go up to 4. So we'll be here. Negative 2 will also be up to 4. And this is good enough to get us started. This is our base graph that we'll compare to. This is just x squared. Now, if we do a few points here for part A, I'll underline this in blue and do it in blue ink. We're going to do 1/3 of x squared. Remember, this f of x is a y value. That's the height of the dots I drew. So here we're going to take those dots and multiply their heights by 1/3 or sort of drag them down. You know, if we just plug in a few points, f of 1, well, if we put in 1 and square it, 1 squared is 1, and then times 1/3 is 1/3. So this red dot here got pulled down. When we multiply it by 1/3, it got pulled down here to a height of 1/3. If we put 2 in, f of 2, 2 squared is 4, and 4 times 1/3 is 4/3. So this dot got pulled down to just a little over 1. Oops. So that'll be 1 and 1/3. And we can see now that this blue parabola is going to be closer to the y, or excuse me, x-axis. The parabola got sort of flattened out. So the blue parabola, the 1/3 x squared, is outside the red parabola. That fraction, when it's between 0 and 1, is going to open the parabola up more. Now let's see, I guess I can use black ink. Green ink doesn't really work well on this background. So black ink for 2x squared. The constant 2 there, it's greater than 1. It's going to make our parabola rise faster. This will make it tighter to the y-axis. Like the origin will be the same, but if we put in x is 1, 1 squared is 1, times 2 is 2. So this red dot on our old parabola is now up here at 2. And that will also be the same at -1. If we put 2 in now for x, 2 squared is 4. This red dot is a height of 4, but now we're going to multiply that 2 and double it up to 8. So I'm going to sort of go way up here, kind of off the graph. And if I connect those dots, the whole number in front of x squared makes our parabola, again, narrower or tighter to the y-axis. So again, the book recommends drawing that x squared, 1x squared, the red graph, just to sort of compare it to the other two. And I see up in the corner, the book has a graph. I'm sure it's better than mine. We'll see here. Okay, the light gray, that's our x squared, and there's our fraction. The 1/3 opens the parabola up. It makes it farther away from the y-axis. But when we make that whole number, the number in front of x squared a whole number, a positive number greater than 1, it's going to make our parabola rise faster, or it's going to make it closer to the y-axis. And what's this? There is a section in the book if you want to go back to review that, section 1.7. Now, in example 1, note that that coefficient a, the number in front of x squared, determines how wide the parabola opens. The smaller value of a, the wider the parabola. Recall back in section 1.7 that the graphs of f of x plus or minus c equals the same thing as f of x plus or minus the constant when it's outside the parenthesis is equal to f of negative x and y equals the negative of f of x. Those are transformations or flips of the graph. You know, we move the graph up, down, left, right, or reflected it. For example, in the figures below, notice how the transformation of our graph x squared can produce the graph of negative x squared plus 1. You know, so we want to do those transformations, especially make sure you do them in the right order. Remember the old high school RV. Like here, if we look at this one, the light gray graph here is x squared, but we're going to make it negative x squared, and we're going to add 1. So high school RV. We're going to do horizontal if there is one first. S are the stretches, R are the reflects, and V are vertical shifts. So here when we negate that, that is going to be a reflection, and then this is a vertical. So we can do the negation first, and I'll do this here on the graph in red ink. If we take this light gray graph and just negate it, it's going to flip it over here. So now it's opening downward, and then this plus 1 is going to vertically bump it up 1 unit. So now it's up here, our vertex, and the parabola is opening down. And I wonder if you did that one backward, would it still work? Here, let me try see if I can do this on the software. Here's our graph opening up in red. If we did the shifts sort of reversed, if we went up 1 first and then reflected it, I guess that would also work because we didn't have some of the other stuff in the middle. So in this case, we would have been safe, but there's other ones. If we have other reflections and stretches and stuffs in there, that order is always important. Always remember that, high school RV. The second one over here, oops, I guess I can just do this. Again, the basic graph of x squared is there. Now here it's horizontal and vertical. These I think we could also do out of order because it's just a horizontal and a vertical. But we want to do the horizontal first, and that is in the parenthesis, that +2. Remember, that's a shift to the left. So that takes this dot at the origin, the old vertex, and moves it over here. And then outside the parenthesis, the -3 is a vertical shift down. So now our vertex is down here. And there might be questions where they're going to ask you where is the vertex of this parabola, and that's exactly how you find it. This one is at -2, -3. If we go back to the equation, we remove this number here and change the sign. That +2 will change to a -2, and this number we keep as it is. -3 tells us where the vertex is. And I'm probably getting ahead of myself. That should be later in the lesson. Standard form of a quadratic equation. Standard form of a quadratic looks like this. I'm just going to rewrite it. I'll put it up here in red. We're going to have some number, just call it a, and then inside a set of parentheses squared is going to be x minus h. And I'm going to put that in a different color, x minus h. H is also just some number, could be anything. And then outside the parenthesis, we'll put a plus here, but remember it could be plus or minus, up or down, some other constant k. So here's our standard equation. X is the variable. The a and the h and the k will just be some numbers. And it says here in our box, well, let's go up above it. This form is especially convenient when you want to sketch a parabola because it's easy to identify the vertex of that parabola as h comma k. Now notice here in here there's a minus. That's why I say when you look at this as a whole, this is always a minus. So you can say I'm just going to change that to the other sign. So if this is a plus, you're going to change it to a minus. If it's a minus, you're going to change it to a plus, and that comes here as part of your vertex. And then this number, if it's a positive or a negative k, you just bring it in, and that's also part of your vertex. That's the y value of your vertex. So in the box, our official standard form, quadratic function, a times quantity x minus h squared plus k, with a being non-zero. This is in standard form. The graph of function f is a parabola whose axis is the vertical line x equals h, and whose vertex is the point h comma k. When a is a positive number, the parabola opens up. When a is negative, it opens down. To graph a parabola, it's helpful to begin by writing the quadratic function in standard form using complete the square. That's why we did that back in chapter P. When am I ever going to need to complete the square? Well, when you're finding the vertex of a parabola, it comes in pretty handy. And then it says, in this example, note that when we complete the square, we're adding and subtracting the square and half the coefficient of x, and we'll go over that here in a minute. Okay. To graph a parabola, it's helpful to write it in standard form. Okay, I guess I copied that twice. Here we go. Example 2, and we always read the directions. Sketch the graph of the parabola, identify the vertex and the axis of symmetry, or the axis of the parabola. So the first thing we want to do is get this into standard form. So let's see here. We're going to factor out a 2. So we're going to have 2. Oops. Ooh, and before I forget, let's when we look at this problem here, we don't want to divide everything by 2 and have the 2 go away. It is part of our equation, but we want our x term here to be a quantity to the second power, so it fits standard form. So if we tried to factor this now, the 7 is going to give us trouble. So what I'm going to do is copy it like this: 2x squared plus 8x, and I'm going to put a lot of space in here and put in my plus 7. Okay, now if I just underline this here in blue, we're going to factor a 2 out, but we're not going to factor a 2 out of the 7. We've sort of put the 7 off to the side. So just what I've underlined in blue, we're going to factor out a 2. So that will be 2 times quantity x squared plus 4x, and I'm still going to leave a space in here. And now I'll switch back to my other ink, plus 7. Now, if you remember back to chapter P, section 4, we did complete the square. So here, this blue part, I'll underline it again in blue, we're going to do complete the square in there. Now remember, we don't want to forget this 2. That is important to the problem. But here, I'm going to do this as 2 times some quantity squared. Remember, completing the square, we bring down our x, we bring down the plus. We cut this number in half, so this will be a 2. Now when we bounce back up here, we square it. So this would be a plus. 2 squared is 4. Remember, in completing the square, we want to add and subtract the same amount. So here, when you see you're adding 4, if you think we're just going to subtract 4, you forgot something. We still got this 2 out here. So imagine, if we were going to get this problem sort of back to the original form, we would distribute this 2. It's going to hit that 4. So this is really a plus 8. So if we're adding 8 here, we're going to minus 8 here. That is the number one mistake in these types of problems. I see it every year, multiple times. If you fall into that little trap, don't feel bad. You will not be alone. Okay, so going on here. So this part is looking good. Let's just clean this up. We've got a plus 7 and a minus 8, so that's a minus 1. Now we are in standard form. Okay, once we're in standard form, it's easy to identify the vertex and the axis, and then that'll make it pretty simple to graph. So now that we're in this form, they're asking for the vertex, and the vertex is just this easy. Vertex, that is an R. I'm going to set a parenthesis and put a comma in there. We know it's an ordered pair. I look at this number as a plus 2, so I'm going to bring it down as the opposite, minus 2. Now outside the parenthesis, this just comes down as it is, minus 1. So there is our vertex. Now when they ask for the axis of the parabola, or just the axis of symmetry, that is just the line x equals, and it's the same as this. The vertex has, or the axis, the vertex has to be on the axis of symmetry. So this is just x equals negative 2. So we can start to come up with a decent graph of this. If they're just asking, yeah, I'll do it like this. Oops. I might need a little more room, and I can shrink this up. Okay, we know our vertex is negative and then negative, so that's going to be a little bit over in the third quadrant. I'll sort of do my graph like this. So vertex, negative 2, negative 1. Here's our vertex. And when we look at the original function, it is opening upward. Opening upward. I wonder if we should get a few more points for that. Let's think here. Just to get a couple more points off this vertex, I don't want to go too far. They're just asking for a sketch of it. Think about our basic graph x squared. It would go through 1, 1 and negative 1, 1 like this. And then if we multiply that by 2, it's going to make it rise faster. So before, when we would go over 1 and up 1 to get to the next dot, now we're going to go over 1 and up 2 to get to the next dot. So back here to this vertex, we can go over 1 and up 1, up 2. So we've got another good point, and from here we're going to go over 1 to negative 3 and also up 2. So there are just a couple more dots to sort of get the how open our parabola is going to be. So again, we went over 2, down 1. So let me draw it in here as a dotted line. Here is our axis. Remember, I said the vertex has to lie on that axis of symmetry. If I graph negative 2, negative 1, it's right here. And that is right where we split our parabola in half. And what do we got here? Oh yeah, here's just the better book graph of that. When they got it into standard form, the plus 2 in the parenthesis moved us left 2, the minus 1 down 1, and then there they got the same dots we did, right here at 1 and 1. Here's some practice problems for you to try. So pause the video, try these. With these, you don't need to get many points. Just compare it, especially with that graph of x squared. So the big deal here are the fractions or whole numbers in front, and if the graph is positive or negative, which way it's going to go up or down. This is just like the second one we did, so you're going to have to put this into standard form and then identify that vertex and sketch it. Okay. For the first one, I'm going to use red for my graph of the basic. So here would be 1, 1. Here would be negative 1, 1. And then 2 would take us up to 4. So we would be up here. Negative 2 also up at 4. So the red graph is sort of our baseline. We're going to compare all these other graphs to this one. All right. The 1/4 in there. Remember, that's like taking this height and multiplying it by 1/4. So this at a height of 1 is now going to be 1/4. We're going to take this height 4. We're going to divide it by 4 or multiply by 1/4. So this point gets pulled all the way down to a height of 1. And we'll have some same thing going on over here. And it's positive 1/4, so it also opens up. So for letter A, something like this. It's more open than our basic graph, and it's also opening up. Now in here, we could do the reflection first. That negative is going to flip us over the x-axis as it's going to open down. And then we're also going to reduce our x or our y values by 1/6. So this point here would get reflected over. It's now at negative 1, but it's going to be cut down by to 1/6 of its value. So it's going to be here at over 1 down negative 1/6. This point here would also be reflected over to negative 4, but it would also be divided by 6. Negative 4 divided by 6, so that would be even less than negative 1. And we would see similar reflected points over here. So this one is now opening down, and it's a very widely opened parabola. It's more open, more wide than what we saw in part A. Now for letter C, there is a fraction there, but don't let it fool you. That's 5/2 or 2.5. So that is a whole number. So, we're going to multiply all our y values by 2.5. 0 times 2.5 is still 0, but this 1 times 2.5 is 2.5. We'll see the same over here. And this 4 times 2.5 is now way up at 10. So that would be up off my graph. This graph is much closer to the y-axis. It's rising much faster because of that whole number greater than 1. Now here we have negative, so this will be flipped over the x-axis. It will open down, and it's also going to be closer to the y-axis because of the 4. So this point here would be reflected over to negative 1, and then it would be multiplied by negative 4, so it's going to be down off the graph. We can't even see it. This point here would be reflected over from, this is positive 4 at its height now. This would be reflected over to negative 4, and then we would multiply that by 4 and take it to negative 16. So this point here would be way down at negative 16. Again, this would be very close to the y-axis and opening downward. Okay, now for the tricky one. So here is our setup. We want to get it into standard form. And to make it easy, we're going to group the 3x squared and the minus 6x. I'm going to put the plus 4 way over here because it's kind of giving us trouble now. And we want to factor out of these terms a 3. So that will be 3x squared minus 2x. And I'm going to leave a little space in there for our completing the square method. And we still got a plus 4. Okay. So over on the left, we want this to be some quantity squared. And we're going to bring that 3 along also. For complete the square, bring down the variable, the sign, and cut this in half. Half of 2 is 1. And when we bounce back up, if we were squaring this out, that would be last times last would be a positive 1. So here, we're not just adding 1, remember, 3 times that 1, we're really adding a plus 3. So to balance that, we want a minus 3. And if we group that, positive 4, negative 3, that is a plus 1. So now we're in standard form. It should be simple to pick out the vertex. V for vertex. I look at this as a negative 1, so that will change to a positive 1. And then this, we keep the sign the same, positive 1. So our vertex is at 1, 1. Our axis of symmetry is the line x equals this same value, x equals 1. So let's come up with a little sketch. Oops, I don't want to get rid of that. And notice here, this is going to be a 3x squared, 3x squared. So that means our parabola will be much closer to the y-axis as it opens up. Or not our y-axis, but it'll be closer to our axis of symmetry. So vertex 1, 1. Let me start a new slide. Vertex is at 1, 1. And now it's going to open up, but it's going to open up much faster than the typical x squared. Here's our axis of symmetry. Now I'm thinking off to the side here, our basic parabola, this would be the point 1, 1. And this would be our vertex. But now our vertex is this blue dot, and instead of going over 1 and up 1, our parabola was 3x squared. So we're going to go over 1 and up 1, but we're going to multiply that by 3. So from this vertex, we're going to go over 1 more and then up to 4. And then, if we go to the left one, we'd also go up 4. So there we've identified where we would hit the y-axis at least. So parabola opening up very quickly. Vertex is at 1, 1. And we have our axis of symmetry. Now to find the x-intercepts of a quadratic function, you must solve the function by setting it equal to 0. Remember f of x, this is our height on the y-axis. When you're finding x-intercepts, when you're crossing the x-axis, your height on the y-axis is 0. So if you get a quadratic, set it equal to 0 to find your x-intercepts. If that does not factor, we could use complete the square or the quadratic formula to find those x-intercepts. Remember, some parabolas do not have x-intercepts. If I draw my coordinate system like this, I might have a parabola opening up. We might not touch the x-axis at all. That's where in the quadratic formula you would have a negative underneath your radical. So that means imaginary solutions. And you don't need the full quadratic. If you just check your discriminant, just what's under the radical, you can figure out if you'll be touching the x-axis at all. So here in example 3, it says find the vertex and the x-intercepts of the parabola. So what we want to do is take the quadratic they gave us, negative x squared plus 6x minus 8, and we want to set that equal to 0. Now, my personal preference, I don't like to factor when my leading term is negative. So what we're going to do, if I draw a sort of set of brackets or parenthesis around that, we're going to factor out a negative. And then that means we'll have a positive x squared, and then a minus 6x and a plus 8. And that's equal to 0. Now remember, when we're setting this equal to 0, we can divide each side by the same quantity. If I divide the left side by a negative 1, negative divided by negative is positive, and then 0 divided by negative is just 0. 0 is signless. So we've gotten rid of the negative, and now something easier to factor. So we did factoring a while ago, but personally I would do this one. Leading term is a 1. I would just say, okay, I know I got to set a parenthesis down here. X squared must come from x times x. And I need two numbers that multiply to 8. I could use 1 times 8, 2 times 4, 3 doesn't work, and if I get to 4, I'm right back to here. And how could I get those to add up to negative 6? Well, negative 2, negative 4. X minus 2, x minus 4 equals 0. All right, now if we have two factors and they are multiplied and equal to 0, we can zero product property. I can set my first term equal to 0 and get x is 2. I can set my second term equal to 0 and get x equals 4. Okay, now if this is all the info we have, I can draw a graph here. And 2 and 4, so here's positive 2 and positive 4. These are x-intercepts. And if I go back to my original equation, negative x squared. I know it's a parabola opening down. Now we could put this into standard form and really nail down the vertex, but if they're just asking for a simple sketch and I know 2 and 4 are my x-intercepts, the graph is going to look something like this. Maybe it goes higher, I'm not sure, but we can at least be assured we're going to go through those points and our parabola does open down. If I bring up this solution here, ooh, well, I guess it does say identify the vertex. So they're not asking for just a simple sketch. They do want more of a graph. Yeah, so let's put this into a standard form then. So let's go back to our original and let's factor out a negative x squared plus 6x. Now here, I'm going to, we're not going to factor a negative out of the negative 8. That's going to stay a negative 8 here. I just factored, well, I guess if I factored a negative out of here, then this 6 should be a negative 6. Okay, we're good. So we factor a negative, out of those first two terms. Oh, and we put the negative 8 out of the way. Now we're going to do a little complete the square here. So down here will be some quantity squared. And I bring down the x and the minus. Half of 6 is 3. And then we bounce back up. Remember, we always add it here. And 3 squared is 9. So here now it looks like we're adding 9, but not really. Remember, we still got this negative out here. So this is really a minus 9. So here we're minusing 9. To balance that, we have to add 9. Subtract 9 here, add 9 here, so it washes out. And now we can combine the minus 8 and the plus 9, and that'll turn into a plus 1. Okay, we can make our graph a little better because we can now find the exact vertex. The vertex is going to be, flip the sign here, that's going to be a positive 3, and this sign stays the same, positive 1. So now our graph is going to get a lot better. So we have our xy axis. I'll stick here more to the first quadrant. And we knew, let's do, here's 1, 2, 3, 4. We know we crossed at 2 and at 4. And now we know our vertex is at 3, 1. So we go over 1, 2, 3. Our vertex is right in between. That makes perfect sense. And we're going to go up 1 unit. So here's our vertex. Parabola opens down. And now I'll pull up the book graph. I'm sure it's better than mine. There we go. Here they drew in the original negative x squared graph, and then it's going to be negative x, that same graph, but now it's shifted to the right 3 and up 1. So the original origin went over 3, up 1. And these points also did the same thing. This was at -1, -1. It went over 3 and up 1. And let me do this point in blue. This would be 1, -1. This one also went over 3 and up 1, and that became the x-intercept. I guess another way you could look at this is if we just took our original graph here and bounced our x-axis down 1. So if I do a blue dotted line here, if we move this x-axis down 1 unit, we can then see these will be our new x-intercept points. This should be our last problem here, our last team huddle. So here, sketch the graph of this. You're going to want to do complete the square, identify the vertex, figure out the x-intercepts. Okay, So pause the video and try that and see if you got it right by starting the video. You didn't pause the video, did you? Okay. Complete the square. This one will be nice. The leading term is a 1. It's not negative, so we don't have anything to worry about there. Let's do it like this. We got x squared minus 4x. I'm going to move the plus 3 over out of the way. So let's see, we're going to come up with some quantity squared, and I bring down the x and the minus. Half of 4 is 2. So when we bounce back up, we're going to square it like we were foiling. Last times last would be a positive 4. If we're adding 4 here, we're going to subtract 4 here. So that makes this 3 minus 4, negative 1. So here is our parabola in standard form. Now it's real easy to pull out the vertex. Vertex will be, switch the sign here, positive 2, comma. This one stays the same, minus 1. So we found the vertex. Now let's get the x-intercepts. They also did ask for those. Remember to find, and let me just move this out of the way down here a little bit. That's better. Oops, get out of there. Remember to find the x-intercepts. We're going to set this original function equal to 0. And this one's real nice because it factors perfectly. So I'm going to sort of just factor this here below. I know it's two binomials multiplied. My leading term has to come from x times x. And what numbers multiply to 3 and add up to negative 4? Well, that has to be negative 1 and negative 3. If I set this first term equal to 0, x minus 1 is 0 means x is 1. And if I set this one to 0, I get x equals 3. So we got plenty of info to come up with a decent graph. We know where we're going to cross the x-axis at 1 and 3. And we know where our vertex is. Our parabola will open up. And let me do this to give myself a little more room. I'll just shrink this down. So we're crossing the x-axis at 1 and 3. I'm going to draw more toward the first quadrant. Let me do it like this. So we know we cross the x-axis at 1 and 3. Here's 1, 2, 3. We cross. We know our vertex is at 2, negative 1. So we would go over 2 right here between and down 1. So we can, and we know we open up. So there's our general shape. We've got our crossing the x-axis. We've got our vertex. There's our general shape. And I guess one more point we could really get easy. Let x equal 0. If x is 0, these terms go to 0, and we would cross our y-axis at 3. 1, 2, put it about right up here. So there's just another point to make our parabola a little better. Okay, I see this must be an old slideshow. Our homework will be on Microsoft Teams. It'll probably just be a WebAssign assignment. I'll see you in the next video.